In this lecture, we will discuss about subgroup. So we have studied about the group. Now we will discuss about subgroup. For defining subgroup, we know that means we have satisfy all the four properties for group. That means we write down the definition of group is G be any non-empty set under the binary operation O. So a algebraic structure is said to be a group if it satisfies four properties. One is closure property, associative property, existence of identity, and existence of inverse. Then we say that G be any group. Now we are talking about the subgroup. So for talking about the subgroup, so we define as let G be any group. G be any group and H be any non-empty subset. Non-empty, that may at least contain one element. Non-empty subset of G. So then H is called a subgroup. H is called a subgroup of G if and only if H itself a group. H itself a group. That means H also satisfy all four properties of the group under the same operation that of G. Binary operation that of G. Okay. So now we talk about the set or subset. So suppose G is 1 minus 1 iota minus iota. Be the example of abelian group. And suppose we are talking about the H we consider as 1 and minus 1. So when we talk about the set, so H is subset of G. So H is subset of G. So that means we can say that G is an abelian group. H is the subset of G. So then H is said to be a subgroup of G. H is said to be a subgroup of G if H satisfy all the properties of group. All the properties of group. So then we can say that this H is said to be a subgroup of G. So we make other subgroup also. So we will discuss later. So first you understand that means G be any group, H be any non-empty subset of G. So this is G, which is a example of group. H be any non-empty subset of G, and then H is called a subgroup. So this H is called a subgroup of G if H itself a subgroup. So this also satisfy all four properties. That means satisfy the closure, satisfy the associative, satisfy the identity, and also satisfy the inverse. So then this satisfy all the four properties. So then H is said to be a subgroup of a group G under the same binary operation that of G. So G we taken the binary operation multiplication. So under multiplication this H is also a group. Okay. So after understanding the definition of subgroup, so we have one theorem. On the basis of that theorem, we can prove that any set is a subgroup of G or not. So very important theorem. We will use directly this theorem. So let G be any group. G be any group. So then H be a subgroup of G if and only if A B belongs to H implies that AB to the inverse also belongs to H. So G be any group, H be any subgroup of G, if and only if AB be two element of H, so imply that AB inverse is also belongs to H. Now we will prove this theorem. So for proving this theorem, so we assume that, let us assume that H is a subgroup of G. H is a subgroup of G. So here we are assuming H is a subgroup of G. So subgroup of G. So it means that H satisfy all the properties of a group. So then it is clear when assume we are assuming that H is a subgroup of G. So then H itself a group. Then H itself a group means satisfy all four properties. So now we consider two elements A and B which belongs to H. So these two elements A or B belongs to H. So A or B belongs to H or H is a group. So then the inverse of these two elements also exist. It is clear? Yes. So since we talk about the B inverse, sorry, we talk about the B. If B belongs to H, B belongs to H, and H is a group. H is a group. So inverse of B is also exist, means also be the member of H. So B inverse also belongs to H. So then B inverse also belongs to H. So now by using closure property, by using closure property, अब closure property के लिए that means we take A, we take this element A or B belongs to H, so B inverse also belongs to H, so we can take as A or B inverse belongs to H. A belongs to H, B inverse belongs to H, which implies that A into B inverse also belongs to H. So this is the first part. That means we have assumed that AB belongs to H, the AB inverse belongs to H. Closure property, you know, A or B belongs to H, so which implies that A into B belongs to H. So this is the closure property. This is the closure property. Here in place of B, we taken as B inverse because we know that B belongs to H. H is the group. So group means inverse of both element. A inverse also exists. B inverse also exists. So B inverse also exists. So we can take this element here also. So A belongs to H. So B inverse also belongs to H. So this implies that A B inverse belongs to H. Now, so this is the first part. We consider the necessary and sufficient conditions. So this is the necessary. Now we move to the converse proof of this theorem. So conversely, let us assume that फर्स्ट में हमने प्रूव किया, अज्यूम किया कि H सब ग्रुप है और ए बी इनवर्स बिलोंग्स टू H होगा. अब नाउ वी कन्वर्जली अज्यूम दैट ए बी बिलोंग्स टू H, the given condition. So this is for converse. Assume that AB belongs to H implies that AB inverse belongs to H. So to prove that H is a subgroup of G. H is a subgroup of G. Subgroup of G. So for proving H is a subgroup of G, so means H itself a. So to prove that H is a group. So to prove H is a group. So for proving group means all four properties satisfied: closure, associative, identity, and inverse. So now when we start with first property, this first property we take as A or B belongs to H. So we assuming that. So we can take as A and A. We take the same element. We can take a same element from a set. A belongs to H, A belongs to H. Means A belongs to H. So which implies that A into और B के प्लेस पे क्या आ जाएगा A inverse. So means AB belongs to H. So A into A inverse belongs to H. So what is the value of A into A inverse? So into A inverse equal to E. So E belongs to H. So here E belongs to H. This means identity. So identity exists in H. Identity exists in H. So we have proved the first part, identity exists. Now, for proving the second, so that may we consider if identity exists, so identity be in another element of H. So and A. E and A belongs to H. E and A belongs to H, which implies that E into A inverse. We are keeping in the mind of this particular thing. We are assuming this thing says AB belongs to H, so AB inverse belongs to H. So we are following this thing. Okay. So EA, so in place of A is E, or in place of B is A. So EA belongs to H, so then EA inverse belongs to H. So EA inverse, by using the definition of inverse, so A into E, that means definition of identity, sorry. So identity says that A into E is equal to E into A is equal to A. So this gives us A inverse. A inverse belongs to H. So this A inverse work as a existence of inverse. So this work as a identity, or this work as a inverse. So that means inverse also exists in the group. So inverse exists in H. So we have satisfied two property. One is identity and second is inverse. Now, when in identity and inverse exist in H, so we move to the third property. Third property we take as A. First element we taken as A. Second element we taken as B inverse belongs to H. If if inverse, second property we have shown that inverse exists. Inverse exists means inverse of both element A and B exist. So when we take as A into B inverse belongs to H, which implies that A into B inverse to the inverse also belongs to H. So B inverse to the inverse. So we have proved a theorem related to that. A inverse to the inverse is equal to A. So this gives us B inverse to the inverse equal to B belongs to H. So AB belongs to H. So this means closure property satisfied. Closure property exists. So that means closure satisfied. So third property, closure satisfied. Now one property we have a associative remaining. So associative property, we write down associative property hold in H also. So some properties we have suppose associative law, commutative law, distributive law. These are the hereditary properties always hold in H. So when satisfy all four properties, so we can write down as H is a group. So when H is a group, so it means that, so hence, if H is a group, so we can write down as AB belongs to H, implies that AB to the inverse belongs to H. For proving subgroup, so we just prove this particular thing. There is no need to prove that closure, associative, identity, and inverse. So just satisfy these properties, then we can say that H is a subgroup of G. Now, we remember some important notes. So one property we have HH. HH is equal to H. We have H inverse. H inverse is also equal to H. We have H inverse. This also equal to H. And we have A belongs to H and B belongs to H. So which implies that AB belongs to H. Okay, so we will discuss later of these properties. So now we move to the next theorem. This is also important theorem which is related to intersection. So this theorem statement says that prove that the intersection of two subgroups is again a subgroup. Two subgroup is again a subgroup. So that means intersection of two subgroup is again a subgroup. So when we prove this theorem, so we assume that let H1 and H2 be any two subgroups. So prove that H1 intersection H2 is also a subgroup of G. You will also write down subgroup of G. So it's also a subgroup of G. So let for A B by using above property, above theorem, A B belongs to H1 intersection H2. AB belongs to H1 intersection H2, which implies that AB belongs to H1 and AB belongs to H2. If two elements which belongs to intersection, that means also belong to the same element. So, but H1 and H2 both are subgroup of G. Both are subgroup of G. When both are subgroup of G, so we talk about this thing. So AB belongs to H1. So that means you can write down as AB belongs to H1. So which implies that AB inverse also belongs to H1. Clear by above theorem. For second, we write down as AB belongs to H2 because H1, H2 both are subgroup of G. So this also satisfy belongs to H2. This also satisfy belongs to H2. So AB inverse belongs to H1 and AB inverse belongs to H2. It means that, which implies that, so AB inverse belongs to H1 and AB inverse belongs to H2. So implies that AB inverse belongs to H1 intersection H2. So we take the element AB, which belongs to H1 intersection H2. We have proved AB inverse belongs to H1 intersection H2. It means that H1 intersection H2 is also a subgroup of G. So hence we can write down as hence AB belongs to H1 intersection H2 implies that AB inverse belongs to H1 intersection H2. So hence H1 intersection H2 is a subgroup of G. So for proving subgroup, just we remember the above theorem, subgroup of G. So this is very important theorem. AB belongs to H implies that AB inverse belongs to H. So H is a subgroup of G. So after defining subgroup, we move to the next definition, that is order of a group, which is very important definition. That is the order of a group. Order of a group. So for order of a group, the number of element in a group. Just we count the number of element. The number of elements in a group is called its order. Is called its order. This is denoted as order of group G. The number of elements in a group is called its order. Or this is denoted as G. Now, how to find the order of the groups? So that means suppose G is equal to 1 minus 1 iota, iota and minus iota. Iota and minus iota is an abelian group. So then the order of above group we denote it as number of element of the group. So how many element in this group is 4. So order of G is equal to 4. Second example, we take a G dash. G dash is equal to 1. Uh, G dash equal to 1 omega and omega square. So this is also the example of group, is also an abelian group. We have already proved also an abelian group. So what is the order of this group? So order of G dash is equal to 3. Number of element in a group is called the order. Third example, we take as G double dash. G double dash is equal to set of integer. Under addition is an abelian group. Plus minus 2, plus minus 3, plus minus 4, plus minus 5, and so on. So is a group under addition. So what is the order of this group? G double dash infinity. So the order of group G double dash is equal to, this is symbol just G dash G double dash. Okay. So order of G double dash is infinity. So you have to remember we take order of group always finite. So remember one important remark. So we take order of group finite. Okay, basically we calculate the order of group of a finite group only. Okay, so we write down this thing is, but we take the order of group only finite. That means this will be 3, 4, so finite elements. That means. Now, after understanding the order of a group, we move to the order of an element. So order of a group, number of element in a group is called order. Now we move to the order of an element. So next definition is order of an element. So for order of an element, so we prove that let G be any group which satisfy all four property, closure, associative, identity, and inverse, and A, small a, be the element of G, be the element of G. So that can be written as, that is A belongs to G. So then the least positive integer n, then the least positive integer n. So remember this thing. We write down in capital letters least positive integer n, such that a raised to the power n is equal to e. A raised to the power n equal to e. So e be the identity. E be the identity. So that means we take least positive integer as n, so which makes the identity, gives us the identity element. So now, for example, how to understand the order of an element. So let g equal to 1 comma minus 1 comma iota and minus iota be a group. सो फर्स्ट इट इज क्लियर जी ग्रुप होना चाहिए और उसके बाद उसका ऑर्डर ऑफ एन एलिमेंट हम कैलकुलेट करेंगे. तो ग्रुप, तो फर्स्ट वी टेक एन एग्जांपल विच इज ए ग्रुप, देन वी कैलकुलेट द order of an element. So we calculate the order of each element of G. So now G having 4 elements. So order of a group is 4. So now we calculate order of elements. So order of an element of G. So G means first element is 1. So for multiplicative, so G is the group under multiplication. It is clear. So under multiplication, you have to remember under multiplication. So what is the uh, identity element for multiplication? 1. So 1 is the identity. 1 is the identity under multiplication. So you also remember this because this is E be the identity. So this equal to 1. So we write down this is a element. So that means a raised to the power n is equal to e. So that means we consider first element 1. So so uh, how to take power or the power which makes equal to 1? So least power means 1. So n equal to 1, 1 raised to the power equal to 1. So this n is said to be the order of an element. So n is called order of an element. So n is called order of an element. So remember. So n is called an order of an element. So this element order. So this means order of 1. Order of 1 is 1. Order of element 1 is 1. Now, second element we take as minus 1. So minus 1 makes us 1. The least power of minus 1 is makes us 1 identity. So that means least power is 2. So the order of minus 1 is 2. Least power of iota makes us 1, means identity. I square equal to minus 1 or I square equal to minus means I raised to the power 4. So the order of iota is equal to 4. So what is the order of minus iota? Gives us 1. So minus iota order is also 4. So minus iota is also 4. So gives us the identity element. So the order of minus iota is equal to 4. Okay. So you remember the first basic thing is that if we take the least power, okay, least positive integer as n, which make equal to identity. Or second important thing you have to remember. So this important thing is that when we write the order of an element, order of a group. So the order of an element A is always less than equal to order of a group. So we can write down as order of an element is less than equal to order of a group. So you have to remember order of A is less than equal to order of G. So that means we can see that the G having order 4. So group having order 4, order of a group is 4. So the elements maximum having a order 4, 4. So order of element is always less than equal to order of a group, less than equal to order of a group. Now, similarly, you can calculate the order of element of order of elements of a group G equal to 1 omega omega square. So this is also group under multiplication. So under multiplication, this is also a group. So under multiplication, this is a group. So the order of group G is equal to 3 because this having 3 element. Now we calculate the order of an element a raised to the power n is equal to e. So that means 1 raised to the power 1 equal to 1. So the order of 1 least power, this gives us 1. Order of 1 is 1. Order of omega gives us 1. So cube root of unity means omega cube. So order of omega is equal to 3. Okay, we know that omega q equal to 1 cube root of unity. So what is the order of omega square? So omega square order. So when we do the power of omega square, so that means omega square raised to the power 2 gives us omega 4 means omega. So not gives us the 1. So that means omega raised to the power 3 also. So this gives also 1. So the order of omega square is also 3. Okay. Now we have very important theorem. The order of A is equal to same as order of A inverse. Prove order of A is equal to order of A inverse. Now we shall prove this order of A is equal to order of A inverse. So for proving this, let we assume that order of A is equal to M and order of A inverse is equal to N. So we take two different orders. So we shall prove that M is equal to N. Now order of A is equal to M. So order of A equal to M. So by definition of order of an element, so by definition of order of an element, order of an element, so this can be written as A raised to the power M is equal to E. So A raised to the power M equal to E. So now, so A raised to the power M equal to E. So take the inverse both side. Taking the inverse both side. So inverse is equal to E inverse because A belongs to the element of group G. Okay, so we group G satisfy the identity inverse all properties. So that's why we write this thing. Okay, so this can be written as this thing can be written as A raised inverse raised to the power M is equal to E. So E inverse equal to E. So E inverse is equal to E. The inverse of an element is equal to E. So this is the equation number 3. So this is the equation number 3. Now from equation number 2, from equation number 2. So equation number 2 says that okay, the order of A inverse equal to N. So order of A inverse equal to 10. So we can write down as from equation number 2, order of A inverse is equal to N. So means A inverse raised to the power N is equal to E. A inverse raised to the power N equal to E. So the value of M and N. So this is from equation 2. This is from equation 2. This is from first equation. So we can say that the value of m and n are not equal, so which may be less than or equal. So here we can say that n is less than equal to m. So the value of n which may be less than or equal to m. So this is our equation number 4. Now again we write down as a inverse to the power n. So this can be written as a inverse raised to the power n is equal to e. So a raised to the power n into inverse is equal to e. So this can be written as a raised to the power n to the inverse to the whole inverse is equal to e inverse. Taking inverse both sides, so this gives us a n is equal to e. So a n is equal to e. Yeah, this thing is the a raised to the power m equal to e. Here is a raised to the power n equal to e. So we can say that m is less than equal to n. So m is less than equal to n. So by using 4 and 5, by using 4 and 5, we can say that m is equal to m. So we have taken the different order, but we say from 4 and 5, we say that m is equal to n. So m equal to n, it means say that order of A is equal to order of A inverse. Order of A is equal to order of A inverse.